Okay, so welcome to the second module on material balance in process metallurgy. So I recommend before you go through this lecture module, it is recommended that you go through the previous one, especially if you want to know about the basics of material balance in general. So here in module 2 I will take a simple case study or an example from blast furnace where one can do a overall material balance looking at what is the input and output from blast furnace. So all of you know what a blast furnace is. A blast furnace is used for production of iron from iron ore, where you have a large furnace almost 25-meter tall, where the iron ore and the coke, which is the basic fuel as well as reducing agent, which is fed from the top, and from the bottom hot blast, basically air with other additions are injected from the bottom, and then this iron ore get reduced, iron oxide get reduced to iron, and it becomes molten, and of course it also dissolves elements like carbon and other minor elements, and it comes out as hot metal, and whatever impurities which is there in the iron ore, coke, all those things along with the fluxing agent, it comes out as this slag. So let us take a very simplified example where a blast furnace is operating with a coke rate of 500 kg per ton of hot metal. This is a typical coke rate in a blast furnace. Of course, nowadays in the modern blast furnace there are other things other than just coke. Coke is quite expensive, so one would like to replace coke with other alternative fuels like coal, injectants like oil, tar, plastics. All those things have been explored, and some of these things have been established now in the plant scale operation. So anyway, here we are taking a simplified case where the coke rate is 500 kg per ton of hot metal, and this per ton of hot metal is one of the basis on which plant operators express many of their operating parameters. So like that, 1200 normal meter cube of dry air per ton of hot metal. Again, it's a simplified case. I have put dry air because it can also contain moisture, and sometimes other hydrocarbons etc. are added, and then you also have hydrogen along with carbon in the furnace. But here we are doing a simple case so that the basics can be brought about, and afterwards the same thing can be extended for other situations as well. And the iron ore contains 95% Fe2O3 and the rest is gangue. The coke contains 85% carbon, and the remaining it goes to the slag. The hot metal contains 4.5% carbon. Again, as I told you, carbon is not just the dissolved element. There can be silicon, manganese, other things, phosphorus, etc. But here we are considering only carbon alone to simplify, to demonstrate the principles. So we are supposed to calculate the composition of the top gas which is coming from the top of the blast furnace and the amount of slag per ton of hot metal using material balance, assuming the whole process is under steady state operating condition. So if you look at, so this is the input as well as the output is represented in the form of a box. This blast furnace is a reactor where you can do the input streams you mark and as well as the output streams, and in principle the material balance can be done, especially if it is a steady state, without looking what is happening inside. One needs to know only the input and output. Based on that, it is possible to do the material or mass balance. So we have to select the basis, and the obvious basis is 1 ton of hot metal. And what has been given is the compositions of the hot metal, the ore, the coke, of course slag. As far as the gangue is concerned, what is the composition of the gangue material in ore as well as the ash content in coke has not been specified, but it has been told that everything goes to the slag, but that is not actually true. As I told you, if silicon oxide is there, some silicon oxide get reduced to silicon and goes to the metal, like that, manganese, etc. But for the present case, all the gangue goes to the slag. And when it comes to composition of condensed phases, it is generally, the convention is it is a weight percent, that is by default it is weight percent, if unless it is specified explicitly that it is not weight percent. And on the other hand, gases are concerned, it is by default volume percent or volume percent. Using ideal gas law, it again becomes the mole percent. So, and as far as the gas amounts are concerned, it is expressed in normal meter cube, that is at 273 Kelvin at atmospheric pressure. What will be the volume? Because volume of gases keep changing with temperature and pressure, so normal stands for standard temperature and pressure, that's why N is used, meter cube. So that specifies the amount of gas in volume at standard condition. So we need to find out the other missing things using the material balance. So in our material balance, we already saw that material balance is like counting apples and oranges. Here we have to basically look at the elements which we count. You can count in terms of numbers. Instead of numbers, we know that 1 mole is one Avogadro number of atoms, molecules. So you can count in terms of moles or gram moles or multiply by 1000 kilogram moles. It becomes easier, especially when you are dealing with chemical reactions. For example, if I take Fe2O3, then I know that one atom of or one molecule of Fe2O3 contains 2 atoms of Fe and 3 atoms of O. So this integer multiplication, so if I take 1 mole of Fe2O3, I can get actually 2 moles of Fe, and suppose if I produce O2 out of it, I can get 3 by 2 O2 or 3 O molecule out of this Fe2O3. That's why it is easier to deal with moles. So we have to do the elemental balance. So let us start with the obvious, the iron balance. Of course, if you look at blast furnace, the most important things are iron, oxygen and carbon. So these are the 3 important things. So let us start with the iron balance, where iron in the input should be equal to iron in the output. As far as the output is concerned, all the iron from the input goes to the metal, because in blast furnace the reducing conditions are so high that all the iron oxide gets converted into iron and almost nothing goes to the slag. So if that is the case, we are talking about 1 ton of hot metal and it contains 4.5% carbon, so the rest is iron. So this is the amount of iron in kg, and then you divide by the molecular atomic weight of iron, so you get in kilomoles. So basically we are counting in, as I told you, Avogadro number. So 17.1 kilomoles, this is the input, and to produce this much you need only half, because you can produce 2 iron from 1 Fe2O3, which is hematite. So you need only half, that's why 8.55 kilomoles. Now we know the atomic weight of Fe2O3, so hence you can calculate what is the weight of Fe2O3. And since the iron ore contains 95% Fe2O3, so the ore amount has to be this divided by 0.95, which is 1437.3 kg of iron. The next is the oxygen balance. So again, the oxygen in the input should be equal to oxygen in the output. The oxygen comes through air as well as Fe2O3, that is iron oxide. These are as far as this problem is concerned. Of course, as I told you, if there are other reduction like SiO2 or MnO, then that oxygen also has to be accounted for, because that oxygen actually goes from the solid phase to the gaseous phase. Basically, oxygen from the furnace, it escapes as CO or CO2 through the gas phase. There is no oxygen, as all the oxygen reacts, so there is no oxygen in the output gas. It will be in the form of CO, CO2, or in the other case it can be even H2O if hydrogen is there. In the present case we have only CO and CO2. So hence whatever oxygen which comes out through air, and I am going to count in terms of O. That's why I put NO air, that means number of moles of O atoms in air plus number of moles of O atoms in Fe2O3 should be the input, that should be equal to whatever number of moles of O in CO plus number of moles of O in CO2. Now we know the amount of air which is being put in, 1200 nanometer cube, and 21% of that is oxygen, and we know that 1 kilomole of ideal gas contains 22.4 in nanometer cube. So I can convert the nanometer cube into moles or kilomoles by dividing it by 22.4. So this gives you a number of moles of O2. Since I am counting number of moles of O, I multiplied by 2, because every O2 gives 2 O. That gives 22.5 kilomoles. And we already know the amount of Fe2O3, which is 8.55 kilomoles of Fe2O3. Every Fe2O3 will contain 3 oxygen atoms, so you have to multiply it by 3, which gives you 25.65 kilomoles of O. So this is the total number of moles of O. This should be equal to the moles of O which is coming out. CO contains 1 mole of O, and every molecule of CO2 contains 2 moles of O. Therefore, oxygen in CO2 should be twice the number of moles of CO2. So that is why the oxygen in the output is NCO plus N2NCO2, which should be equal to the total O added coming in through air as well as Fe2O3, and that comes to 48.15. So now we have 2 unknowns, so we need another equation to solve this, and obviously you can see that both the other element which is there in this equation is carbon, so you need to do the carbon balance. So again one can do the carbon in the input and carbon in the output. Carbon in the input in the present case is only coming from coke, and as far as output is concerned, it goes through as CO, CO2 as well as carbon, which get dissolved in the hot metal. These are the outputs. So we know 500 kg of coke, 85% is carbon. Dividing by 12, it gives you the kilomoles of carbon. So that is a carbon input, which comes to 35.42 kilomoles, which should be equal to carbon in CO, carbon in CO2. Again, one CO2 contain 1 C, 1 CO contain again 1 C, plus 45 kilograms per ton of hot metal divided by 12. So that gives you the kilomoles of carbon which is there in the hot metal. So this is the oxygen balance, this is the carbon balance. So we have two equations and two unknown. This is what generally comes in most of the, this is one of the most important balances one needs to, one encounters, whether it is blast furnace or it is in steel processing, any of those things, because we'll have CO and carbon and oxygen coming, so that balance becomes very important. So then we can solve this, and from there you will get the amount of CO2 as 16.48 moles and CO as 15.19 moles. Of course, generally the CO by CO2 ratio is on the order of 1. Here actually CO by CO2 is less than 1, which is actually too good an efficiency. Maybe our coke rate was actually less than what should have been. There are other considerations which one can see. There will be lectures on blast furnace risk model where you will be able to appreciate why the CO-CO2 ratio has to be close to 1. Anyway, for the time being, let us take this example, and you can see that CO2 is slightly more than the number of moles of CO. So now we can do the rest. We have basically done the iron, we have done the oxygen, we have done the carbon. So that gave the most important balances, elemental balances one needs to do. Now the rest can be done, because we know this amount of Fe2O3 and 5% is the gangue, so which comes to 71.9 kg, and similarly 500 kg, 425 is because 85, so the rest is gangue. So these two gangue, all of those goes to the slag, so these two add up to the slag. Of course, if, as I told you, if SiO2 or MnO etc. get reduced, then that much amount of SiO2 etc. has to be taken out from the slag. So when you do the SiO2 balance or MnO balance, that needs to be taken into account. In addition to it, if there is a fluxing, which is often there, that also need to be accounted for the slag. And this is the metal, and we know what is oxygen, and the rest has to be nitrogen, and nothing happens to the nitrogen. So whatever is the, if there are 42.32 kilomoles of nitrogen, which correspond to 1185 kg, the same amount of nitrogen has to come out, and this is the CO2 and CO which we calculate. So from this, these moles can be, all of them can be converted into kilograms by multiplying those with the corresponding atomic weight. So once you do that, the input as well as the output has to get balanced. Quite often this need not be the case when you actually take the plant data and try to do these kinds of balance. It may be because some of the measurements may be wrong. That can be, for example, CO2 measurement. If something is not okay with that, you will get an inconsistent mass balance. Or it can be also that something you have not accounted for. For example, there is a lot of dust generated from the blast furnace. If you don't account for it, that can give a significant deviation. The input and output will not match. So in a way, looking at material balance, and not only material balance, also the energy balance for the whole process, that should be the first thing one should do, so that one can actually find out what kind of, how the process performance is, and what kind of remedial action, or where is the scope of improvement. All those things can be got out from doing this overall energy material balance along with energy balance. In the plant, generally it is recommended to represent all these things in the form of table. It's like for an accountant, it is like a balance sheet. Basically, material balance is exactly like accounting for different things which you put in and things come out. So it's exactly like an accountant's job. So it can be represented in the form of table, and you can see that the input and all the species which are involved, all those things have been put, and in kg, so looking at this table you can make out, for example, carbon, where it has been put and where does it go, or Fe2O3, how does it come, where all it goes. Of course in this case it's a much simplified case, but there can be some species or elements which may come through different inputs and come out through different outputs. So all those things can be very nicely analyzed using such a table. So let me stop it here. So this is the simple overall balance for a blast furnace is presented here. In the next lecture I will also present the overall simplified overall mass balance or material balance for basic oxygen furnace.